problem tells us it's undergoing SN2 process, and we have to draw the product of this process, SN2, and our first job is to identify which one is nucleophile and which one is substrate. And looking at this, substrate is the one that bears the leaving group. We have iodide, the halogen here, which is a very excellent leaving group. So I identify this as substrate. And the one next to it has to be nucleophile because we have lithium that tend to form the positive cation, and then in turn that's going to create our ring structure here on that specific carbon to be nucleophilic center. So we're gonna have nucleophile, and if I redraw this, gotta look like that. And that lone pair with a minus charge is going to attack, since this is SN2, it's a one-step process where the nucleophilic attacks and the leaving group, loss of a leaving group, happens at the same time. And we can draw this with a substrate stationary and the nucleophile attached to it, but then that's going to change the shape of our ring, the dithion ring, so it's easier for us to keep the nucleophile as it is, and then just rotate a substrate to 180 degrees and then just stick it up there. So let's just keep our nucleophile intact. Okay, now the nitrogen is going to be on this side, so we're going to have nitrogen over there, and then our oxygen is going to be here, and then that nitrogen has bulky substituent. So this answers part A. Now let's move on to part B. The nucleophile exhibits a 6-membered ring with 2 sulfur atoms called dithion ring. Explain why the dithion ring in compound 3 exists primarily in 2 conformations, while the dithion ring in compound 2 exists primarily in 1 conformation. So in order to solve this, we must discuss the ring flip. Starting from compound 2, I can also draw the flip version. Okay. So if I do this right, so you remember that this carbon takes if we call this 1, that's gotta be 2, and our sulfur here gotta be actually 6. 3, 4, 5, 6, and then they come back to 1. So okay, let me redraw this. So if I flip this, okay, that's gonna be here, it's gonna be carbon 1. And then next to it, this is gonna be our carbon 2, but we don't have carbon this time, we have sulfur. And then 2, 3, 4, 5. Okay, 2, 3, 4, 5, and then 6 is gonna be here. Okay, now you notice that the carbon 1, where is it? Okay, this is our carbon 1 right there, this carbon I'm talking about. The substituent is below the ring, so that means, okay, this side must be downward. I'll also draw so for now I'm gonna draw the two equal lines, but you'll see that one is more favored. Okay, so you gotta remember that when we have the bulky substituent that's in axial position, it's gonna create 1,3 diaxial interaction that actually hinders our structure. I mean our this hinders the energetically favored form. So we wanna try to keep the bulky sterically hindered substituent on the equatorial position, and energetically it favors this structure more than that structure. So that's why we only see one conformation in general. However, when you take a look at our compound 3 we just formed, you have to remember that either way it's gonna create bulky on the axial position. So you see that we have a bulky up here, so I'm gonna write the R for now, and let me use a different color so that you are less confused. Okay, for simplicity I'm gonna call it R1 here and then R2 here. So if I do the ring flip, okay, now that carbon now becomes this carbon, so I will also draw the orange points so that you know which one I'm talking about. Okay, so that axial R1 is gonna be here, and the R2 is below our ring, but that's gonna be the axial now. They kind of switch the position, and both structure or both ring conformations have one axial and one equatorial. Therefore, both are equally probable. So that answers our part B.